Welcome back. So today's lesson, Chapter 10, The Restless Ocean. We're going to continue on our ocean theme. Last time we introduced you to the geography and the composition of the ocean. And so now we're going to look more at the circulation of the water and the movement of the water and how, of course, that is going to erode, transport, and deposit various landforms, coastal erosion, coastal deposition. And so that is sort of what Chapter 10 is going to take us through. So let's get started on that. The movement of the water. So ocean water movements, the surface circulation. There's actually two forms of circulation in the ocean. One, we talk about the surface circulation, and then the deep ocean circulation as well. A little bit different processes going on to get the motion of the water at depths as opposed to at the surface. So here it's talking about the surface circulation. The ocean currents. These are masses of water that are going to flow from, of course, one place to another. And there is sort of a gradient with our water motion, and it's going from places of warm water to places of cooler water. So there's a gradient within the ocean as well. But surface currents are developed from friction between the ocean and, of course, the wind. The wind is your primary driving force that moves the surface ocean water. So that's the primary driving force for the ocean surface circulation, those surface currents they talk about. Friction between the ocean and really atmospheric winds is producing currents at the surface. And it begins to really follow the atmospheric motion. And so we get these huge, slowly moving gyres as the winds are pushing the water along, the surface of the water along. We get several developed kind of circular or gyres, they call those, with the surface waters. And so here are the five main surface gyres as we talk about. North Pacific, South Pacific, so we're looking pretty much straddling the equator, north of the equator, south of the equator, and so they're speaking about Pacific Ocean here, north and south of the equator, north and south for the Atlantic Ocean as well, and of course Indian Ocean circulation as well. So these are the major circulations, surface circulations, and of course it is related to the atmospheric circulation. We'll be getting to that here, probably our next chapter that we'll talk about. We're going to be beginning the atmospheric circulation. So you can't really get away from talking about the ocean without talking about the atmosphere as well. And so kind of this picture that I had back in the introductory chapter of all four spheres interacting, that is not more true than, say, a beach scene here, where of course you do have the atmosphere acting on your ocean circulation, that surface circulation, and then of course the interaction of the waves along the beach, so the geosphere in there as well. So the ocean really is at a very dynamic interface between those various spheres of the earth. And so that surface circulation is directly related to the primary driving force is the winds, okay? Think of that, related to the atmospheric circulation. And here are a bunch of those gyres that they were referring to, and we can kind of see the pathways that they're showing us. And we'll see they've kind of got it color-coded. I don't know how well that's going to show up for you. But of course the equator is right along here at 0 degrees, of course, latitude. And then we've got north of the equator and south of the equator. The red colored arrows are warm currents. The blue are cold currents. But they set up, as you can kind of see here, we've got the warm Gulf Stream current flowing towards the north. This is out here in the Atlantic. Kind of bringing the warm waters from the equator and moving upwards towards the north, where, of course, closer you get to the poles, the colder it is. Bringing them water back, cooler water back towards the equator. So we do get this circulation, this movement of warm water going towards colder regions, colder water coming back down towards warmer regions. So you get a circulation, a nice circulation of the various temperatures that way. And so yeah, little gyres setting up. There's several of them here. The main ones, of course, North Pacific, South Pacific. Notice that one goes in a counter clockwise motion and clockwise motion. Again, clockwise, counterclockwise motion within your different hemispheres, northern hemisphere, southern hemisphere, and that's related to something we do call the Coriolis effect, and we'll talk about that here in a second. So these are the main gyres, slow moving, huge masses of water. You've got one out here kind of in the North Atlantic, I'll mention here, where you don't really get any good defined currents in there. One's called the Sargasso Sea, okay, kind of out there in the northern Atlantic. Of course, yeah, you've got your Gulf Stream going this way, right? Canary Current going this way. Right, but you're left with sort of this mass out there that doesn't really have well-defined currents. This one in particular is called the Sargasso Sea. No well-defined currents out there, and so a lot of, unfortunately, our garbage kind of gets from the ocean, kind of gets stuck out there, sort of in a dead zone, we call it, and the Sargasso Sea is certainly one of those. But your main gyres, right, but then out there towards the middle, not a lot of circulation happening. One in particular is called the Sargasso Sea. Maybe make yourself a note about that little area. So Sargasso Sea. Okay, so our main gyres though. Now really, other than the wind, which would be our main primary driving force, we have here sort of secondary, other than wind. Well, the most significant factor next to wind is this, what we call the Coriolis effect. This comes from and is due to Earth's rotation. So I've got my little Earth here, a little styrofoam ball here. But of course, Earth is rotating in a counterclockwise direction, okay? And as you have any sort of a fluid, air included, and this will become very important in the atmospheric circulation, the Coriolis effect does. But because the motion of the air, the winds, actually does drive our surface circulation of the ocean, well, it's interrelated. So we have the Coriolis effect. And the thing to note about it is as your wind is moving, let's say, from the northern hemisphere, right, the counterclockwise rotation, okay, is rotating kind of underneath it there of the direction of the wind, and it causes a veering to the right in the northern hemisphere. And this motion, if you were to say coming from the southern hemisphere, actually does a veering to the left. So there's sort of an opposite per hemisphere, but the to the right in the northern hemisphere, winds are deflected to the right of their path in the northern hemisphere, and the winds are deflected to the left in the southern hemisphere. And it really has to do with the rotation of the Earth, you know, beneath the winds, okay? And of course the ocean as well, being a fluid too. And so it's a very important factor of, you know, pretty much moving warm waters to cooler waters, just like it does warm air to cooler air sort of thing as well. And I kind of had this as a little extra document here. I don't believe this is in your PowerPoint, but the Coriolis effect is due to the rotation of the Earth and it does cause winds at different latitudes, right? So different latitudes, north or south of the equator there, to travel at different speeds, okay, that rotation. So it's essentially zero at the equator, okay, no motion, let's say, from at the equator, to being fastest at the poles. And so this will set up, it will cause moving objects like wind, right, to kind of veer to the right of the in the northern hemisphere, so clockwise we would say, and causes objects to veer to the left, right, of their direction in the southern hemisphere, or counterclockwise, let's say. So it will set up, as we were seeing with those gyres on that previous page, maybe I can put that back in there, that is why we're seeing the deflections like we're seeing them on this, in our gyres. So here we are in the northern hemisphere, and so winds are coming along. They're going to be deflected to the right, okay, in the northern hemisphere. Any which way they're kind of going, they get deflected to the right, okay, kind of in that clockwise motion. Here they're getting deflected to the left of their path, and so we set up a counterclockwise kind of motion in the southern hemisphere, and it all has to do with what's happening in the atmosphere. And again, we'll talk more about this when we get into the atmospheric circulation, but that's known as the Coriolis effect. So after wind's the primary factor, the Coriolis effect influences the movement of the ocean waters, known as the Coriolis effect. And it is very important in surface currents that it can affect kind of the climate of an area, especially these coastal regions, because depending on what type of a current you have, do you have a warm current like the Gulf Stream? Do you have a cold current like the cold California current or something like that? Of what kind of water? That will influence your climate for sure. Currents from low latitudes moving into higher latitudes, these warm currents transfer heat from warmer areas to cooler areas, and it really, coastal locations can be affected by these currents. Are they warm or are they cold? And it will affect their climates. So here is an example of the Gulf Stream current, and of course the Gulf Stream is a warm current, and so it gets all the way up there. Here's, you know, New York and such. This warm current, and they kind of call it a current because it meanders similar to like our streams, and so they call it a Gulf Stream in their current. This is a warm current. Actually brings warm waters way up by the British Isles, up there near England and the British Isles. So for their latitude, they actually have a little milder temperatures than what they would have if we were strictly going by latitude, northern latitudes being colder. The warm Gulf Stream actually moderates their climate that they have in their location. So yeah, water can very much have a moderating effect on the climate. So depending on, you know, do you have a warm current or maybe do you have a cold current? Really, they can affect in the coastal areas. Not so much, you know, when you get into the mid-continental regions. There's other factors there, but definitely. So let's say an influence of cold currents is most pronounced in the tropics, or maybe even during the summer months in your middle latitudes, on what kind of weather, how you're going to moderate your weather, your climates, they say. Also, we can get upwelling. So upwelling is the rising of cold water from deeper layers, okay? It's most characteristic along the west coast of the continents. This is actually where water is veering away from the coastline. A water mass is coming away from the coast. That allows for water to come up, the deep water to come up from the bottom, which is much colder, really high in nutrients. We do call this upwelling. of the cold water rising from the deep because of that motion bringing water away from it. So say if I kind of put my hands in a bathtub and would spread my hands apart, water would come up from the bottom there. That's an upwelling. Well, if we're getting a veering of our stream, our Gulf Stream, whichever one it is, of your gyre, pulling water away from the coastline, that is going to allow for water to upwell. And we do see that along the west sides of the coast of continent, South America, of course North America, out on our west coast, but South America is one where the fisheries industry does so well because of this upwelling. It's pulling away water from that coast, allowing for the upwelling of nutrient-rich waters to come up and, of course, feed the fish in there. So upwelling is something that does happen. And here's a little picture of upwelling happening. Okay. Of course, off the coast of Africa here, and this would be off the west coast of Africa. So we've got your surface current coming along, the winds causing that to veer away from the coast, and that does allow for upwelling to happen. Here, they're just showing the chlorophyll concentrations there, and you're seeing that they are much higher right in through near the coast where the upwelling is occurring. And of course, all of that is allowing for photosynthesis of that nutrient-rich water in there. So you do see sort of these algal blooms along those upwelling regions because the waters are so rich in nutrients. So that was all the surface circulation. Okay, but we also need to talk about the deep ocean circulation. This has a different, of course, it's away from the effects of water or the atmosphere, the winds. The deep ocean circulation is due to some terms that we've talked about before, the temperature and salinity kind of properties of our ocean water. So the deep ocean circulation is a response to these density differences. So of course, temperature can have an effect on the density of your water as well as salinity. And if you recall, salinity was the amounts of dissolved materials, those salts in your water. The more dissolved materials, the more dense your water will be. So salinity, yeah, density, it would increase with increasing salinity. And with temperature, cold water would be more dense. So density, we'll just write that up for you. Physical property. Density is the mass per unit volume. It's a physical property of matter and including water. And so kind of the overriding factor or the primary factor in density of water is going to be your temperature. That's kind of even more so than the salinity. It kind of overrides the salinity factor. But your cold water is going to be more dense, and it has to do with the arrangement of the mass per unit volume. Cold water, just like cold air, is going to be having those molecules more densely or tightly arranged per unit volume, so you would be able to get more mass in that volume, in that space of volume. And so the colder water is going to be more dense, right? Warmer temperatures, that's the same thing as warmer air. You've got the molecules moving a little more rapidly, kind of bouncing off of each other, so they're not as tightly packed in a warm mass, volume of water versus even a warm mass of air, right? Same type of thing with the water and the air going on, because we'll talk about the circulation. So in that case, it becomes less dense. Warm water, warm air, less dense. And so that does have an effect on the density. Salinity as well does, because the more solids you have, more mass you have per unit volume of water, well, the greater the density is going to be. the less dissolved material, right, the less dense, so the less saline or saline, they would say. So two factors going on in there that are going to control the density of your water. Of course, more dense water is going to want to sink. Less dense is going to want to rise. And so we're setting up motion with this method. So deep ocean circulation. So the temperature factor, which is the overriding factor, the more significant factor is temperature. And salinity, they're both working together, right? We've heard those terms, salinity introduced last time. But this is known as the thermohaline circulation. So deep ocean circulation is controlled by thermohaline circulation. So thermo standing for the temperature, haline, right? The haline is standing for the salinity amount. How much salt, and halite was our sodium chloride table salt. So halo, right? The haline. Circulation. So those two terms kind of put together does drive our deep ocean circulation. Okay, so that deep ocean circulation is really referred to as the thermohaline circulation. Okay, and so in looking at kind of what would be our coldest waters, our most dense kind of water sort of thing, most water involved in deep ocean currents begins kind of at the high latitudes at the surface, because let's think about the Antarctic waters. The Antarctica waters are like the most cold and the most salty waters. So these are going to be your densest water bodies, the Antarctica. Think of the Antarctica there in the southern hemisphere. Very, very cold and very, very salty water. Why it's so salty or saline is because of the sea ice that forms out there on the water, right? That's going to leave behind any of the salt and really concentrate the salt. So that's like some of the most dense water is going to be your Antarctica waters. So most involved begins at the high latitudes at the surface. So that water's going to want to sink, right? And then it begins circulating. Here we kind of have like a little conveyor belt there, a simplified model of the ocean circulation, kind of like a little conveyor belt. Travels from the Atlantic Ocean through the Indian Ocean and to the Pacific Ocean and back again. So it's starting and it sinks, working its way cold water, then it warms and it rises, right? So we are getting a circulation. Of course, this can take a tremendous amount of time for this to occur, even 500, 2,000 years maybe for that water to finally resurface. But here's kind of that idealized conveyor belt model of ocean circulation. So very, very cold water down here, subsurface flow. Of course, this would be more towards the, Antarctica down here, some of the most coldest, densest water of all. And it begins to flow, deep ocean kind of circulation. Then it starts to get up here kind of towards the equator region and it begins to warm, and so the water will rise to a little higher level, right? And that water gets flowing and it's a warm surface flow, okay? And it will wheedle its way up and through. Here we are way up here by Europe and Africa, and then of course the Arctic Ocean, very, very cold. That water's going to want to sink again. So again, we get the subsurface motion happening, the cooler subsurface and then the warmer surface flow. So this is the conveyor belt that kind of talk about here on really how we are moving deep ocean circulation of water. And again, cold going towards the equator, warming and back down again. So we do get a nice circulation in there. By these density differences, these are driven by density differences, okay? That deep ocean circulation. So keep that in mind. There's two kind of means of circulation happening surface circulation driven by the winds mainly. The winds get it going, and then Coriolis effect also kind of controls those as well. And then the deep ocean circulation, the thermohaline circulation, motion, so this restless ocean that they refer to. It is always in motion, for sure. Okay, so now we want to look at the characteristics and the movement of the waves, that energy that is going to be traveling along, kind of that interface between the ocean and the atmosphere, our waves. And waves, you know, we're going to look at the parts of the waves, and then we'll start looking at sort of some of the effects and the work of the waves, that energy on that interface, the ocean, land, atmosphere kind of interface, very dynamic interface there. So yeah, our waves, energy that's traveling along the interface between the ocean and the atmosphere, right? The atmospheric winds are what's kind of driving the surface circulation. And so they derive their energy and their motion from the wind. So those atmospheric circulations are very important in driving this. So some of the parts of our waves that we talk about. You want to talk about the crest. So waves do have sort of a sinuous nature to them, and the uppermost part of that wave motion in there is called the crest. The lowest part is known as a trough. Okay, crest to trough, and surely they'll have some pictures in there for us in a moment with some of the terminology that they're going to be talking about. We'll get a nice picture. And so here's some terms that you'll need to kind of get under your belt there. The wave height is going to be the distance from crest to trough. Okay, and so you have something like this, right? There's crest, there's trough. Okay, so going from crest down to trough, right? That's going to be your wave height, crest to trough, okay, or trough to crest, whichever way you want to think of it. But that's the wave height. Wave length would be the horizontal distance between two successive, if I went ahead and put another crest up over here, okay, another crest, from crest to crest, that is a wave length, right? So this would be the horizontal distance between successive crests or troughs. I mean, we could go trough to trough, right? But those are called the wave lengths, okay? Wave period, so the time interval, how much time interval from one full wave to pass a fixed point. Say I had a stake or something, a post there. So we got one wave to pass by to the time that it takes the second wave to pass by. So the time interval for one full wave, say one crest to the next crest, let's say, to pass a fixed position. That's known as the wave period, okay? Here's our picture, okay? So here we go, and you can see kind of that orbital motion. It does sort of have an orbital motion of the water particles in there. So yeah, we're going from crest to trough, that's a wave height. Crest to crest, that's a wave length, okay, that they're talking about there. And here, if you're looking out there kind of in ocean, open water out there, notice how we get to a certain point where we can no longer actually feel any water particle motion. It says negligible water movement. So you get to about below 1/2 the wavelength. It's kind of like the base of your wave base. It ends up being 1/2 of your wavelength. That's your wave base. Okay, so 1/2, I'll write that in there somewhere so you can see this. 1/2 of your wavelength. So I'm using a little symbol. It looks like a backwards Y or upside down Y. But that stands for lambda, a Greek letter that we use for wavelength. But 1/2 that wavelength is known as the wave base. Wave base. 1/2 the wavelength. So whatever your wavelength is, 1/2 of that, okay, you would have negligible water motion. You know, say if you were swimming in the water and you wanted to get away from that swaying of the wave action, you'd have to swim down 1/2 whatever the length of your wavelength is. Okay, and that's known as a wave base. Distance from wave crest to wave crest, which is wavelength, right? Water particle becomes negligible. Water particle motion becomes negligible. That's your wave base. Okay, and that's mentioned right down there on your PowerPoint. Okay. Okay, so the waves can change. They're, you know, the height, the length, and the period can really depend on your three things here. Well, how fast is your wind blowing? Wind speed. That can have an effect on just how high the waves are going to be, what your wavelengths are going to be, and of course that would be the period would change as well according to wavelength. So wind speed has a factor in there. The length of time that the wind is blowing, so kind of the duration that the wind is blowing. You know, is it a long period? Is it a short burst? That's going to have an effect as well on your wave height, length, and period. And something we call fetch. And so fetch is the distance that the wind is blowing, okay, over. Amount of distance that the wind is traveling across. That's the fetch. So as the water is traveling, the water passes energy along by moving in an orbit. So a little circular type of motion, and the energy is what's getting translated down the line. And your water particles are actually just kind of bobbing up and down in these orbits, this circular kind of motion that we see. And so here's a waveform, and there's a little toy boat in there to sort of show you that orbital type of motion happening. So waves coming up, the little toy boat is going to bob up and down. It'll move up a little, forward a little, down a little. So it sets up this orbital kind of motion, and it'll just bob kind of up and down in the water as the wave energy is passing by. The actual water particles are just sort of moving in a little circular motion. Okay, so it's the wave energy that's getting transported through. And so how we're going to see some changes then depends on what the topography, there's that term again, the topography or the shape of our ocean bottom. So as you near the shore, that is going to actually get a little shallower as you're getting closer and closer. Your water depth will get a little shallower as you're getting towards the beach, okay? And so way out there in deep water, right, here's kind of the base of your wave, but the wave is unhindered because you're out in the deep ocean water. It's not getting changed out in deep ocean water. Things start to change as you get closer to the shore. Once that wave, okay, actually what we say touches bottom or feels bottom right here, okay, that is going to change your, you know, wave velocity is going to slow a bit. This will allow the water to kind of pile up. It will increase your wave height. It will decrease your wavelength. See how these waves are getting closer and closer together now? And the wave heights are getting higher as you're touching bottom, feeling bottom there, right? That will change. Also notice how instead of this nice circular orbit, your motion becomes more elliptical, okay, in the orbit. More elliptical, less circular. And it's like your wave is falling forward a bit. So this bottom part of the wave is getting a lot of friction, so it's slowing down. But the top part of the wave, it's it's going unimpeded. So it's kind of going at its same speed. This part's getting slowed down. And so your wave starts to kind of lean and fall. And eventually it gets way too top heavy. That angle of repose, remember that, becomes too steep and it crashes forward. It falls forward. We call that a breaker. And it breaks forward. Or the surf zone, where the waves have finally crashed forward and are breaking, they say. So that wave depth, of course, wave base, okay, again, is 1/2 the wavelength in there. And so water begins to touch bottom at an equal depth to about 1/2 its wavelength. Again, 1/2 its wavelength. And it will begin to touch bottom or feel bottom, and it will fall forward, and of course that's what we call the surf zone. Okay, so just remember that 1/2 the wavelength, sort of for a calculation. Not necessarily going to do a calculation, but just kind of keep that in mind. Your surf zone will actually begin where you get to 1/2 of that wavelength. Okay, and that will be your surf zone as well. Okay. So things do change as that water makes it towards the shore, because the bottom, the topography of your basin is changing along the way as well. Okay, so let's look at some shoreline processes now of our beaches. We love our beaches and the shoreline. So beaches are composed of whatever material is available that's getting eroded. So where it's coming from, it could be coming from rivers bringing sediments. Of course, mountain terrain could be bringing sediment as well. So sometimes they do have a biological component. You can get seashells and coral sand beaches. So really it's just whatever material is making its way to that particular beach shoreline in there. And of course that material does not stay in the same place. Even though the beach might look the same from day to day, know that that material, if it's a sandy beach, know that that material is moving every single day. Motion. It could be a completely replaced beach. It looks the same because the material that's replacing it looks the same. So really, it is not staying in one place. It is continuously in motion as well. And so we did kind of learn a lot about our streams, what are the work of our streams, the work of our glaciers. We already looked at some of the turbidity currents beneath the ocean surface, but here we're at the interface of the shoreline and the water. And definitely you are going to get that material eroding, transporting, and depositing that material down the line. And so we'll be looking at some erosional features as well as depositional features, but we do get changes that are going to occur when the wave moves onto shore. So lots of little things. Beaches are definitely that interface of the air, land, and sea. So a very dynamic location for us. But wave erosion caused by the impacts of that pressure, of that pounding kind of material. It will break down the rock material, and this is what is supplying the various types of sands to our beaches, the wave erosion, those crashing into the beach there, those breakers or the surf zone. We have some sands here. I actually had various kinds of sands that we could look at. We could kind of do some hopping around, beach hopping kind of thing. But right here they had some contrasting type. It's not all that brown sand that we see for our beaches, and these are two very contrasting ones that they're showing us here. But you can get those sugary beaches, those quartz sand beaches. You can get, the white beaches of like the Bahamas as well. But here's a couple pictures they have. The black sand, which is basalt. And we've kind of talked about that oceanic crust and the basaltic material from the basalt. But here, I don't know, again, how well some of these will show. Here we've got some of that basalt, a bit of vesicular basalt, and then this black sand. Hopefully I'm not in the way there. The black sand of Hawaii is coming from that igneous rock known as basalt, right? And so you get these black sand beaches. It's very nice. It's really fun to handle these beach sands here. So that would be from Hawaii. Think of the Hawaiian Islands. They are created from igneous activity, the basalts, the lava flows, and so that igneous rock basalt, B-A-S-A-L-T, that's an igneous rock known as basalt in black. So the black sands of Hawaii are from the igneous rock basalts. That's one that they're showing us there, that basaltic kind of lava in there. The other one there, up there in California, there's actually several kinds there in California, but very pebbly. Let me find my Pebble Beach, coming from Pebble Beach, and these are pebbly material. These are very large pebbles that they get there from the wave action, just sort of, and they're kind of very well rounded. Here's one, kind of showing how well rounded they are from the wave action, rolling that material around and around. Right, my head out of the way here. Various pebbles, okay, from the Pebble Beach. Wave action, smoothing those out. Yeah, so you can get pebbles. California, think of California Pebble Beach, right? Get you a bag of Pebble Beach material from there. Very different from your fine kind of black sands from Hawaii. Some other ones, oh, let's see. Let's go on down around, let's do Padre Island Beach, for example, from Texas, right? The kind of a lot of iron coming from this region, west of the Mississippi River. Had a little bit of that from Padre Island in there. Kind of gives it that brownish kind of tinge to it from the iron that's being eroded off of the land, and of course all that's trying to make its way down there to the Gulf of Mexico. So sort of a brown sand, maybe what you think of when you think of a beach. But this one is Padre Island. It's a barrier island that we'll talk about our barrier islands and how they're kind of forming, kind of a depositional form. Oh, let's see. We could keep on going around to, here's one from Gulf Shores, Alabama. This one is more of what we would call a quartz type of a sand, quartz material. And here's actually a piece of quartz in there. Quartz is a mineral, that silicon dioxide mineral. When we talked about our siliceous oozes, those biogenous sediments, those organisms are secreting a siliceous coating, so silicon dioxide or a quartz type of oxide on them, or a quartz type of a shell on those. So these are more of a quartz type of a sand coming from the Appalachian Mountains. So again, it's beaches or whatever the material is that it has to erode from. And so this would be from, say, the Gulf Shores of Alabama, okay? Those quartzy sand beaches, they call those. We can move on around. What else do I got? Oh, I have Key West, Florida. And you see a lot of seashells in this one. So a lot of that, this would be calcium carbonate. There's a nice little seashell in that one coming off of there. But all those seashells kind of get broken up from the wave action, and that of course ends up on your beaches, right? You can also get actual work of a beautiful fish known as the parrotfish. I wonder if I got my picture of the parrotfish. Out there in Bahamas, doing some work for us. Where'd that picture go? Here he is, the beautiful parrotfish. They have sort of these chitinous beaks. Almost looks like a beak of a parrot, so they call it a parrotfish. But what that fish does, a beautiful fish, he's out there and he's munching on the coral. Now the coral has little zooxanthellae, little organisms that the coral or the fish likes to eat and feed on. So it's actually munching and crunching on all of the coral. Of course, that goes through the body of the fish, this beautiful fish, and goes out as excrement. And so, yeah, those beautiful white beaches, those coral beaches of the Bahamas are actually fish poo. But of course it gets sloshed around in the water and the sun cleans it up nicely. But here we go. We've got a little bit of the coral sands from the Bahamas here. Okay, and it's got a little bit of sort of the pinky little grains of pink kind of algae in it as well. It's quite beautiful in there. And so this is some from the Bahamas, those beautiful coral beaches, thanks to the work of our parrotfish, really working on the coral. So yeah, biological animals can actually get in on the action of creating some of our beaches as well, right? And including, of course, the wave action as well. Okay, let's see. Here they go, and they're showing you some in your PowerPoint there of the Bahamas and the beach sand there as well. The beautiful white beaches, the coral beaches from the Bahamas again. Action of that little critter, that beautiful parrotfish as well. Okay, so that would be kind of a calcareous sand, the calcium carbonate type of a sand in the Bahamas. Okay, so really we would expect to see, of course, the black sands in Hawaii, that igneous rock basalt, pebbly beaches in California, along some of their coastlines. Really the brownish sands from, say, Galveston and Padre Island, going on over east kind of the Mississippi's, the Appalachian Mountains. They're going to give you those quartzy sands, kind of the sugary sands they call those. And then on over you can get some more of, say, the shells types, and then of course the Bahamas are going to give you the coral types of beaches as well. So really it's pretty much your beach material is going to be from whatever material is eroding away from the land, maybe the action of some biological activity to act on your beach material and break it down. So our beaches, right? Now, wave refraction. So the refraction, to refract, does mean to bend of your waves. And so depending on what's happening with atmospherically, your winds, right? Because the winds are the primary driving force of your waves, and that's going to get the waves in motion. Well, they're not all coming parallel to the shoreline, so your waves may start out as an angle, right? Coming in towards the shore. Let's say the shore's up here by the blackboard, and here's my wave coming along. Well, this part of the wave is going to reach the bottom of the sea floor there, towards your shoreline. It's going to be a little shallower. This part of the wave is going to hit first. So your wave's coming along. It's going to hit here. This part of the wave is going to slow, but the rest of it's going to continue on unimpeded, right? So you end up with your wave kind of coming in, eventually parallel to your shoreline. Okay, so it will refract and bend, right? Depending on the topography at the bottom of the shore there. So the wave usually is going to arrive parallel to your shoreline. So this does really act to get that wave energy getting concentrated against the sides and the ends of, say, a headland. Say you had a protrusion. A headland is kind of a protrusion sticking out on your shoreline. Well, those are going to come on in. The wave erosion is actually going to create sort of straightening of any irregularities you might have. And of course, this is over a tremendous amount of time that this is occurring, but it will act to straighten out any protrusions you might have in your shoreline. So they're saying wave erosion will straighten an irregular shoreline over time, though this can take some time for this. But yeah, you're kind of getting a refraction of your wave. Here's a little picture that might help that a little bit. So seeing how that wave is kind of coming in at an angle to the shoreline. There's the shoreline. It's coming in at the shoreline at an angle. Okay. Well, this part of the wave is going to reach the shore, the bottom of that shallow shoreline sooner than this part of the wave. And so that's why you're getting the refracting to where it then becomes parallel as it comes in on up to the shore. Well, what that tends to do is squish the water. It will squish the water down this way, down coast. And that is known as the longshore current. So that wave's coming along, right, going like this, and this part of the wave is doing that. That's going to squeeze that water down the line and whatever material along with it. And so that's known as the longshore current. And as the water goes up, okay, and meets the shoreline, you get little sands moving up and back, okay, kind of the swash, and then it comes back in this zigzag kind of motion that's known as beach drift. So those sand particles are moving back and forth, kind of down the shoreline as beach drift, and of course the longshore current as well. So you get a net movement of your sand grains. And so that's why I was saying that the beach that you're looking at today is not going to be the same beach tomorrow. It might look the same, but all those particles are continuously in motion. So that's kind of our longshore transport that happens, keeping things moving kind of down the line there. Oh, and so they are referring to how that wave refraction is going to kind of smooth out and level off any irregular structures you have on your shoreline. So here is like a headland, a protrusion. Well, eventually that's going to erode that all the way back, right? You're going to get erosion here. That's where the most force of the wave energy is acting on it. And then you'll get some deposition and some beach deposits out towards the side where the velocity is not so great in there. But over time, that is going to straighten out your coastline. Okay, and again, they're talking about the beach drift, so sediment going up, right, and coming back down in this zigzag pattern, little particles moving back and forth. That's known as the beach drift. And then the longshore current, that was out in the surf zone where the crashers or the breakers, the surf is happening. Those waves are crashing forward, right? And it flows parallel to the shoreline. So of course, eventually, yeah, that is going to squeeze that water and push it in a parallel fashion to the shore. And of course, that's going to move substantially more sediment than your little zigzag of your beach drift, though. Okay, so longshore current, yeah, is moving a tremendous amount down the line. Definitely the longshore current parallel to the shore. That's the one that's moving most of that. Okay. So this is in the surf zone, right? It's the surf zone current, and it's really termed the longshore current, moving that material right in there through the surf zone area, right? It parallels the coast. Okay, and here we're seeing the beach drift, right? That zigzag pattern, right, of the individual sand moving back and forth. There's your beach drift. Here's your longshore current, right? So that's squeezing that along, squeezing the water on down. So beach drift versus longshore current in there. Beach drift's kind of a zigzag motion. Well, you can get the winds coming in at all directions, and so you can get something that we call a rip current. Now, sometimes it's a misnomer that they call it a rip tide. It has nothing to do with the tides that we're going to talk about at the end of the chapter, which is an astronomical phenomenon, but these are known as rip currents. Now, rip currents, so you can have a longshore current coming in this direction, but you can also have one coming in the opposite direction. So when your two longshore currents merge or converge, that water is going to go right on back in a stream. You see all that whitish kind of color in there? So we had a longshore current coming this way, one coming from the opposite direction. They merged. Okay, that energy gets forced out towards the sea, so seaward. And that, if you get caught in the rip current, that is a very swift stream of water, right? So converging longshore currents can actually pull you out into the water, and no human, not even our Olympic swimmers, are strong enough to swim against a rip current. Okay, so you're certainly not going to be able to swim, back to shore in that current. What you need to do is go one way or the other, but swim parallel to the shoreline. Okay, eventually you're going to get out of that rip current that's trying to pull you out farther and farther into the sea. So go parallel to the shoreline, swim parallel, yell for help, whatever you need to do, but swim parallel, and then you would be able to, once you get out of that rip current, be able to swim back up to the shore. So these are very dangerous. And when the winds are like that, and the likelihood that you're going to get merging longshore currents to create a rip current, they will put out the red flags. And so those red flags are a warning that rip currents are happening, or the favorability of them happening is, evident. And so you need to stay out of the water when those rip current red flags are up. And this was a while back, but there were some students that went out to Gulf Shores, Alabama, kind of as I guess it was a spring break thing, but 20 these kids had to be rescued from that because of the rip currents along the Gulf Coast, risky kind of area. And a lot of the lifeguards had to rescue people from this. But of course, you've got to pay attention to the warnings. They had the red flags up. So you do have to heed that. So I don't know if y'all are doing any spring break or the summer, but definitely pay close attention to that, because this can be very, very dangerous. So here, is all these signs. You'll see these signs everywhere, trying to help you understand what a rip current is and how to get out of one if you happen to get yourself into one. You've got a longshore current that way, so merging longshore currents, all that energy is going to take you out, straight on out, farther and farther into the ocean. And so you would want to escape by swimming parallel to the coastline, and eventually you're going to swim out. They're fairly narrow streams in there, so that you could swim. If you swam, parallel long enough, you would get right out of there and be able to, swim right back up to the shore. So don't panic, but yell for help. And certainly, if there's any red flag warnings, don't be going out in the water. Pay attention to those warnings. Okay. But yeah, converging longshores can create that rip current that we talk about. Okay, so let's look at some more here, some erosional features. And again, our oceans will erode, transport, and deposit sediment, just like our streams, just like our glaciers, right? So here are some erosional features. We see a lot of this out on our west coast. Think California out over there when you think of this type of erosional features. So got things we call wave cut cliffs. And so this is wave action cutting into a cliff to the point where you can start to get a platform, so sort of a flattened out region, a wave cut platform. And then if you get a series of these, we call them like a marine terrace. It's almost like a little stair-step looking structure where you'll have, you know, a fairly steep region, then it'll flatten out, you'll get another one, and it'll flatten out, and another one, and another one. Because over time, the erosion had taken place and you've been getting changes in sea level, or maybe the land is uplifting or lowering, a variety of combination of that, and can create the marine terraces. So those are some erosional features. With the headlands, and so remember the protrusion of the headland. Well, if you get enough erosion coming in on the sides of that headland, you can actually create a sea arch to where it erodes all the way inward and creates a little arch out of that. And hopefully they'll have some pictures for us here. But that's a sea arch. A sea stack is when it actually erodes and becomes so unstable. Your sea arch becomes so unstable that the top part of the arch falls in and you're left with just these little, you know, protrusions that they call sea stacks. Okay, and so these are all a series of, you know, erosion over time that the wave action can create. And so here the wave cut platforms, the marine terrace, right, the wave cut cliffs, so the action of the waves cutting into the cliff. You can get a flattened out platform, they say, and you can actually get marine terraces, so almost like a stair-step type of a feature. You're going to see that, yeah, your California coastline, the spectacular coastline, you're going to see that erosional shoreline erosion happening. The wave cut platforms, the wave cut cliffs, and the marine terraces. Think of, you know, California. Here's another location in California, Torrey Pines, and so you can see again your marine terraces, wave cut platforms, but just think of California coastline for those erosional features, the wave cut platforms, the marine terraces, right? Another beautiful coastline there. Torrey Pines, California. I don't know if that's in your PowerPoint or not, but sometimes I add a few here and there. And this is Baja Peninsula in Mexico. So as a headland, you know, a protrusion of land from the shoreline, and the wave action's acting on it, right, coming in on it, and it actually erodes through the middle of that, and you're left with what they call a sea arch, okay, the sea arch. Well, if over time the erosion kind of really makes this unstable to the point that this part becomes too heavy and can't be supported, that'll like collapse down in, and you're kind of just left with the stacks out here. Okay, at one time they might have been connected, right? But then that arch kind of fell and left you with a stack. They call it a sea stack. So beautiful terrain out there, Baja Peninsula in Mexico, with the sea stacks and the sea arches, all erosional shoreline processes, these little structures that get left behind. Normandy, France, so we have another one. Oh yeah, right here. And these are the white cliffs, so these are those chalk cliffs. If you remember, the chalk was made of those little calcareous oozes, right? The little calcareous calcium carbonate shells, the little microscopic organisms, right? The chalk, right? You remember that? The calcareous oozes. So these cliffs, these white cliffs in here are all chalk. But look what erosion of the ocean has done. There's another one up over there. And then there's a sea stack there. So you've got the sea arch and the sea stacks from Normandy, France even in that example. Oh, and here's really showing that sea arch. Oh, we got a golfer out there. I don't know what he's trying to do, but there's the arch, right? The sea arch there. Normandy, France, the beach of Normandy. Yeah. So those were all erosional features of the wave action. Well, here are some depositional features now. Something we call a spit, but this is sort of a little hook, a hook kind of a buildup of sediment, so a ridge of sand extending from the land into the mouth of an adjacent bay. And you usually get, yeah, like a little hook at the end that kind of hooks towards the land. That's called a spit. I think I had a little diagram of all these different ones they're talking about. Well, if your hook continues to kind of go towards the bay to the point that it actually closes off the bay, right? It just continues to build out and build out. You can get a sandbar that would completely cross the bay, or maybe the spits are coming from both sides and eventually it will block that off completely, and it's called a bay mouth bar, okay, for that, again, depositional feature. Here we have something called a tombolo. This is a ridge of sand that connects an island to the main shoreline. If you've got your island in there, and as the waves are coming in, they're kind of going out around the island, so right in front of the island, it's pretty calm water, which allows for deposition and the sand to build up. And so sometimes that sand can build up a ridge straight on up to the mainland. So a tombolo, we call that. But I don't know how well these will show up. But something like a spit, right? So you get a little bit of that sediment, a little hook kind of shaped protrusion that's protruding kind of back into the bay in there. That's known as a spit, kind of a hook shaped projection of sand that's coming from the beach, and then it goes back into the bay. That's known as a spit. Well, right, so you can, maybe get a spit coming from both sides and it completely blocks off your bay. That's called a bay mouth bar. Okay, a bay mouth bar there. Here was the tombolo. So you had some sort of an island or something here, but that the velocity has slowed down in front of that to where it builds up that sand ridge known as a tombolo. Another one, they talk about a barrier island. The barrier island is a ridge of sand that has built up, over time when maybe sea level was a little lower, and you could build up your beach a little higher there. And then, of course, when the sea level rose again, you get some water that gets kind of trapped back behind in here, a lagoon. So we call those barrier islands, okay? Paralleling the beach, we were talking about Padre Island, South Padre Island, Galveston, along the Gulf of Mexico. You see a lot of barrier islands there. So these are some depositional features that we can see. We also have some of these barrier islands to our east coast as well, Cape Hatteras, North Carolina kind of thing. So those were some of those features: a spit, a little hook-shaped kind of projection, a bay mouth bar, right? Actually would block off your bay, a tombolo, a little ridge of sand in there, right? Here's another bay mouth bar, a view of a spit and a bay mouth bar. So there's a little hook projection. Again, this is on our east coast, Massachusetts coastline. There's a little spit projection. You can see the little hook. Here is where we've had the bay mouth bar. So it actually had sand build up and block off the bay. And you can notice in here that they have kind of cut through here, okay? They need to kind of dredge that out because, of course, they need access to the ocean out here. This is the bay back in there, but they kind of need access for their ships and their boats to get out into the main ocean there. So they kind of have to dredge that region out kind of keep that open because it keeps wanting to continue to deposit in there. So a little baymouth bar and a spit. So we do see that along the east coast as well. So a little spit, kind of a projection, kind of a hook-shaped little projection there of a spit, they call it. And so that's a depositional feature as well. And there's another baymouth bar. So you kind of have your bay back behind and then the ridge of sand kind of trapping that bay back behind. So that's a baymouth bar. There's a picture of a tombolo. So you kind of have a main little island back out here, and then you've got a nice little walkway where sand has built up, because right there in front of the island is not a lot of velocity of the water. So again, when velocity drops off, you do get the deposition happening. So that's a tombolo, a little ridge of sand kind of connecting an island to the mainland. Okay, a tombolo. We might have a barrier island, right? So they're kind of low offshore ridges of sand that parallel the main coast along there. So mainly along the Atlantic coast, as I mentioned, Cape Hatteras, North Carolina, our East Coast, and our Gulf Coast plains as well. So think of Texas, Padre Island, Galveston, as well, Texas along and through there. You'll see these barrier islands, little depositional kind of features. They definitely parallel the coast, and they originated in several ways, and I mentioned already one where a change in sea level, very important. So let's say the last ice age where all the ice up on the land, right, with the glaciers, that lowered sea level a good 200 feet. And so you could get a different shoreline at that point. And so it kind of built up a ridge of sand where the normal beach was. Well, then when water, kind of rose again as the ice began to melt, go back to the ocean, sea level rose, some of that water got trapped behind our original beach, and new sand built up. And so the barrier islands kind of are derived in this manner, kind of ancient sand dunes, if you will. And so those got built up, and they kind of act as barriers, so they call them barrier islands, because they tend to receive the brunt of these storms like hurricanes. They'll end up actually protecting your shoreline when you have a barrier island. But the problem is a lot of people want to build on these barrier islands. We love our barrier islands. And so here's one. This is along the Gulf Coast here, right? Texas. We got Corpus Christi. We got many of them here. South Padre Island, along and through there, going along a barrier to that Texas kind of coastline in there. But yeah, we love our barrier islands. We love to go visit those. But the problem is people build on those, okay, with devastating effects, because again, they do get the brunt of these storms, okay? So probably even before we started to learn a lot about what the role and dynamics of a barrier island is, people tended to build on these with devastating effects. I mean, they'll lose their homes in these storms. So, all right, let's take a look at how we try to stabilize the shore, because we love our beaches. We love to visit our beaches, and we want there to be beach material where we when we go to visit a beach. And so some things that can really influence erosion and how good your beaches are going to be are, well, your proximity to sediment-laden rivers. Those rivers, as you remember, the work of our rivers, they do bring a tremendous amount of load, suspended load, bed load, and such, dissolved loads, sediment-laden rivers. So if we're putting up dams that are trying to control our rivers, we're actually blocking that sediment from making its way ultimately to the ocean. So proximity to sediment-laden rivers, you know, how close is your beach to a river, sort of thing, or are you putting up a dam to your river? So a lot of that's going to affect, you know, just how much shoreline erosion you're going to have. The degree of tectonic activity, so plate tectonics, you know, is your land moving up? Is your land moving down? And in kind of coincidence with this is what's happening to sea level. Is sea level rising, sea level falling? A lot of that's going to have a lot to do with your stabilization of your shoreline. Topography and the composition of the land. So there's that term again, topography. What is the shape of your basin kind of thing? What is this, you know, are you in a mountainous cliff-like area? So what is that topography of the land, the composition of the land? What's your material of your land that's coming from it? You know, was it the quartzy material like we see in Alabama kind of thing? Is it the, you know, the Mississippi River material that we see a lot of with the brown sands, the ironstone sands? So is it the pebbles for Pebble Beach, that sort of thing, composition of your land? Is it the black sands of Hawaii, sort of thing? Prevailing wind and weather patterns. And so again, atmospheric circulation, that's what sets up the ocean current, right? The surface current. So what's that prevailing wind pattern and your weather pattern? Configuration of your coastline. So do you have, you know, the protrusions, or is it one that's been eroded and sort of leveled out over time? So what's going on with many things that can kind of influence the erosion? So trying to stabilize the shore. Of course, your Pacific coast, as we mentioned, California, we've got characterized by relatively narrow beaches. They're backed by steep cliffs and mountain ranges. So think of your wave-cut platforms, your marine terraces, your wave-cut cliffs kind of thing. That's pretty characteristic of your Pacific coast. So think of California when you think about, you know, those wave-cut cliffs and that sort of thing, the marine terraces. But a major problem is narrowing of the beaches. So sediment for the beach gets interrupted if you put up dams and reservoirs, as I mentioned. That sediment's not making its way to what could potentially be beach material. So you're going to end up with some rapid erosion occurring along beaches like that, where the sediment gets blocked. So definitely something to think about if, you know, we want to keep our beaches. Dams will have a impact on that. Some things that we're trying to do, responses to the erosion problems, because we love our beaches. We want our beaches. They try to add some things, some hard stabilization, they say, is where we're building some structures in various ways that will try to cut down on the impact, that wave impact, hitting our beach, okay? And so some things, here's some names for you. The first one there is a groin. So a groin is made perpendicular to the beach. Here's your beach. And they put these sort of perpendicular, okay, structures. They're built at right angles to the beach, and they are designed to trap the sand. And it works okay. Let me get you a picture here, because I don't know that we have a very good picture of this in the PowerPoints. But that idea of a groin. So here's your shoreline. And here we have these structures, right, built, we've got several of them here, built perpendicular or at right angles to the shoreline. And so what happens is, as the longshore currents coming along, right, parallel to the beach, well, here we have it this way, that longshore current creating the movement of sediment, right, in that direction, you are going to get a place where you're going to get erosion, and then the velocity drops off and it will trap the sand right there. You'll get erosion up in here, velocity kind of drops off, and you'll get a buildup or deposition of sediment. Here you've got the erosion, but there you've got the deposition, okay? So you end up with kind of a funny looking beach, but some places you have a more narrow beach. Other places you got a little wider beach, and then it kind of repeats itself. So depending on where you live, if maybe your home's right there, you're not getting quite as much of a beach. If you're over here, you're getting a little more of a beach. But anyway, they're trying to stabilize the beach and trap whatever sand they can, because that longshore drift is going to move it on down the line and erode, right? So this is kind of that idea, building those perpendicular or right angles to the beach to trap that sand that moves parallel to the shore. So that longshore kind of current. That's the idea of a growing, okay? Those little parallel ones there. All of these are going to try to, act to lessen that erosion. Breakwaters, so these are barriers that are built off of, away from the shoreline, but parallel to the coast, right? They're actually parallel to the coast. Here's your coast. There would be a barrier, a breakwater. And it really does protect their boats from the breaking waves. So it will end up, the wave action is going to hit the barrier and then come on in around much more slowly. And so a lot of times they're going to park all those boats right in front of the breakwaters, right? But that will act to build up your beach in front of a breakwater there. Those are called breakwaters. Okay, that's probably going to show us a few things here. Well, here's your example of your drawings, and so you can kind of see how, they built those perpendicular to the beach. And yeah, here's it's a little eroded, but here you have a little bit better beach. Erode, deposit, erode, deposit. So that's kind of the idea of the growings, is to help trap that sand so we can save as much of our beach as we possibly can. And there's the breakwaters. So out over here, you've got these breakwaters, okay, again, there are structures built parallel to the shore, okay? You can see maybe some little white dots there. Those are some boats that are parked there because the water's not as turbulent right in through there. So it's kind of a quiet waters in through there, but look at the beach. Look at that beach right, behind that breakwater. The beach is built out nicely because that water does come in much more gently. It's impacting the breakwater, the structure, and expending its energy on the breakwater, and then it's coming in, a lot more gently. And so you are really allowing for a buildup or growth of your beach right in behind a breakwater. So yeah, they'll kind of build those breakwaters to help in that effort there. And a nice place to kind of park your boat there. It's a little gentler current going on. So there's an idea of some things that they try to do. And of course, seawalls are another thing. Armors the coast against the breaking waves. A lot of times, over time though, your seawalls are going to get eroded as well. They'll start to get cut in because of the wave action, and you have to go back in and repair those quite frequently. So, often they're not real effective, but hey, we're trying to do what we can to stabilize that ever-changing, ever-in-motion shoreline, right? That beach is never the same from day to day. So we're trying to do that. Another one that they do, it's an alternate to hard stabilization, but it's something that they have to continuously repeat to do over and over here, but they're happy to do it, honestly. One called beach nourishment. They actually add sand to the beach. So they go out in a tugboat and they'll just kind of like vacuum up the bottom of the ocean, right? The sediments on the ocean a little ways off of the shore there. Bring that up with a tugboat, bring it back to the shore, and we'll lay that out and kind of redistribute the sand to kind of nourish, they call it, beach nourishment, by actually adding the sand back, going out and dredging it out a ways off from the shoreline and bringing it back up to the beach. So kind of beach nourishment, they call that. I think there'll be a picture of that here in a second. And maybe relocating your buildings away from the beach. That's very costly to do that. So a lot of them will actually pay in their taxes to pay for the beach nourishment, because you want your visitors, right, to have the beach. That's why they're coming there. They want to enjoy the beach. So, yeah, erosion problems along the U.S. coast are a little different from one side kind of to the other, but shoreline erosion problems are different along opposite kind of coasts. So depending on, you know, the prevailing winds, what type of terrain we have, all those other factors that affect erosion are a little different on the coast, each coast of the United States. I think they're going to give us a picture of Miami. So over there in Florida, if you look, this is a picture of Miami Beach before the beach nourishment, right? So you've got, oh, look at all the hotels out there. And I mean, what? They've got the groins in there, but there's basically no beach, you know. And so in order to, you know, draw your tourists in, you've got to do that beach nourishment. People are coming to enjoy the beaches, right? So see, we just barely have any bit of a beach there. So this is Miami before the beach nourishment, and that's more like it. There we go. So now we have our beach after the beach nourishment, and that's what we're wanting to go and visit and pay to get, you know, those hotels right on the shoreline there. So yes, these proprietors will pay, and they're happy to pay because they want their tourists to come, right? And so the beach nourishment process there is just pulling. Here it is, the little tugboat out there that sort of vacuumed up and sucks up the sediment from the ocean floor a little ways out, and then brings it in and puts it up on the beach and redistributes it. I mean, the water will redistribute it in a short order. You got all the seagulls out there because that also brings up a bunch of the seafood, right? The little snacks for the, you know, the crabs and different things that the seagulls love. So a little bit in trying to stabilize our shorelines there. So the Atlantic and the Gulf Coast, of course, have those barrier islands we talked about. But the barrier, as the name kind of says there, they do face the open ocean. They do kind of act as a barrier from the main shoreline. They are going to receive that full force of any storms, the hurricanes, right? Out in this area, the Atlantic coast, the Gulf Coast, we get those hurricanes in those locations atmospherically that brings them into these regions. So developing on those barrier islands, people will build on there. We want to have our beachfront, you know, homes. And so people have developed on there more rapidly than our understanding of the barrier island dynamics. And so when a storm does come along, the barrier island's doing what it's supposed to do, be a barrier to the main land, but people build on there, and with devastating effects. I mean, they get wiped out. So you can't build on a barrier island and not expect to have a hurricane hit at some point. And this is Galveston Island, the barrier island on Texas. This is after Hurricane Ike in 2008. All of these little concrete slabs, I don't know how well you can see that in the video, all those concrete slabs were once homes, right? You got a few homes, so I don't know, they did okay, right? But the majority of those homes were wiped and just destroyed there. But you'll see people, they'll build again because they want to be close to their beaches. And so it's kind of like building on a floodplain. You've got to expect that a flood is going to come along once in a while, right? And I'm sure their insurance is really, really high. If you can afford the insurance, I suppose, go ahead and build on a barrier island. But eventually, yeah, you're going to get hit by these storms with these barrier islands, right? Okay, so coastal classifications, we got a couple main types of coastlines, we would say, or shoreline classification. So classification is based on change with respect to sea level. So do we have rising sea level? Do we have lowering of sea level? And it can actually be a combination of what's happening to the land. Are we getting an uplift of the land? Or is it a drop in sea level? Or are we getting a rise in the land? Or a rise in the sea level. So a combination maybe of both of these, but these two main classifications, there's two, emergent and submergent coasts. So an emergent coast is caused by either an uplift of the land, so tectonically the land is lifting up, or you're getting a drop in sea level. Out on our west coast, we actually have the scenario where there's an uplift of land. So it's like the land's coming up out of the water, right? And so either one of those, uplift of land or drop in sea level, can cause what we call an emergent coast, coming up, above kind of the layer there. And on an emergent coast, you are going to see, like we see out in California on our west coast, you're going to see those exposed wave-cut platforms, the marine terraces, the wave-cut cliffs that we talked about, those erosional features. Here's the Big Sur, California, Highway 1, spectacular view of the coastline. This is an emergent coastline. So think of the land coming up or sea level going down, but in this case on our west coast, it's the land actually coming up, plate tectonics taking place. So yeah, an emergent coast, you're going to see your exposed wave-cut cliffs. You're going to see, of course, those platforms, those marine terraces are all going to be found along the emergent coast. And just think of California when you think of an emergent coastline, right? Okay, submergent coastline. So you, can think of, our East Coast for that, the opposite side there. So here, submergent, so submerging meaning it's kind of going below sea level here. The land adjacent to the sea is subsiding, or your sea level is rising. So in either case, the ocean or the sea is encroaching and submerging the land. And so that's known as a submergent coast. These are going to be highly irregular shorelines. They're going to see some things known as estuaries. These are drowned river mouths. So the rivers are coming from the land and the mouths of them are being drowned. So the encroachment of the seawater coming up because the sea level is rising is drowning those river mouths. And so, highly irregular coasts with numerous estuaries are frequently characterized by a submergent coastline. And yes, we can think of, our East Coast. So they've got a nice picture of that, of the United States. We kind of have opposite types of coastlines here in the United States. But often they're Chesapeake Bay, so they've kind of blown that up just a little bit in there. Delaware Bay as well. See all the rivers coming from the land, right? They're coming from the land. The Atlantic Ocean is encroaching on that, and so they do call those estuaries or drowned river mouths. But think of the East Coast of the United States for a submergent type of a coastline. So two kind of categories for our coastlines, and we've got one on each type on each of our coasts. So West Coast has the emergent coastlines, and the East Coast has the submergent coastlines. So okay, so let's look at tides. Now tides are going to be motion of the water, right? The ocean water, the elevation of it. And this is a daily cycle, the tides are. And so this is an astronomical few forces that are happening that creates the daily tide cycle. So this is caused by the gravitational forces exerted upon the Earth by both the moon, mainly because the moon is closest in distance to us, and the sun. But the sun to a lesser extent because it's like really far away, 93 million miles, right? So moon and sun, though, both of those gravitational forces. And so they are the result of gravitational pull by both the moon and the sun. So here I have my little demo model here, Earth, Sun, Moon model. Here's the sun, here's the Earth, here's our little moon. And so the cycle of the moon, of course, takes about 30 days to make one complete orbit around the Earth, right? So as it does that, it goes through the moon phases. And so we'll look at just 4 positions here that, of course this is all going along throughout the month, but 4 main positions of the moon. This one here, from our perspective here on Earth, we actually don't see the illuminated side of the moon, and we call that the new moon phase. That's like the beginning of the cycle of the moon phase. We would call that new moon, okay, this position. Then in its orbit, the moon going around the Earth. Okay, this would be a first quarter. About another week later, 7 days later, we would actually see the right half of the moon illuminated. That's what we call first quarter. Another 7 days goes by, okay. We see the full disk of the moon illuminated. That's known as a full moon, this alignment. So you can see that alignment. They're all in alignment, so parallel to one another. And then another 7 days, make sure I get that turned right. You can see from our perspective here on the planet that we would see the left side, left half of that disk, okay, illuminated. We call that a third quarter moon phase or a last quarter moon phase. And then, of course, another 7 days, and we are back to new moon. So it takes about a month, right, for the moon to go in its cycle around its orbit around the Earth. So you're seeing a changing of the position of the moon and the alignment of the sun, Earth, and the moon. So what we talk about are these various tides, right? So when you have an alignment where the sun, the moon, and the Earth are all in line, you're getting an extra pull of gravitational forces from the moon and the sun. It's like they add together and they pull on the Earth and the Earth's water, of course, and create a little bit of a bulge, right? As they are going through. And then, of course, Earth is rotating in its daily cycle and rotating through those bulges. So we end up with a bulge here and a bulge here, okay? Giving us a little bit higher tides in those bulges as we rotate through in our 24 hours. And then less bulge here and here sort of thing. So we're getting higher highs and lower lows kind of things, and we're getting a really strong pull at a new moon and full moon. When you have this geometry of the sun, moon, and Earth, right, all lined up, you're getting an extra pull, extra gravitational pull. We call those spring tides, okay? We call those spring tides. You're getting higher high tides and lower low tides, so that sort of change, okay, between high and low tides, daily cycle, are like really exaggerated in the spring tide, we call that. So this does occur during new and full moon, right? Here was the full moon, here was the new moon with this alignment, parallel alignment. The gravitational forces get added together, and you're getting especially high and especially low tides, okay? So higher high and lower low tides, meaning a larger or the largest daily tidal range, higher highs and lower lows, because of all that extra gravitational pull. That's a spring tide, right? The largest daily tidal range, right? Higher highs and lower lows. These are known as spring tides, and this has nothing to do with the seasons, the spring, no. This happens throughout the year, and it's related to sort of that monthly tidal cycle, okay, during new moon and full moon, okay, this kind of orientation of the moon and sun and the earth, okay, largest daily tidal range, higher highs and lower lows, low tides with our spring tides, okay. And so again, they're showing the moon, earth, sun positions there. When you have that either at new moon or at full moon, right, one or the other. This picture's putting them both in the same picture here, but we only have one moon. We don't have two moons. So it's either new moon phase or full moon phase when this occurs, right? So twice out of the month, right? A couple weeks apart, or well, 1 week apart, right? Couple weeks apart, because you've got new moon, and a week goes by, you got first quarter, and then another week. So 2 weeks later, you have full moon. Okay, so that's what we call a spring tide position. The other one is called a neap tide, N-E-A-P, neap tide. So this has the least tidal range, okay, between high and lows, okay, and that's where you're going to have either in the first quarter moon position or 2 weeks later in the third quarter moon phase. Okay, so at first quarter or third quarter moon, so look at the orientation of the sun, earth, and moon. They're at a 90-degree angle. So those gravitational forces are offset just a little bit. They're not adding together. They're opposing kind of each other. Of course, the sun's really far away, but they do oppose. They're not adding those forces together. When you get sort of this perpendicular or right angle geometry, okay? So it counterbalances that gravitational pull just a little bit to where then your neap tides, get that to kind of come up, your neap tides, first and third quarters of the moon, gravitational forces are offset, so your daily tidal range is the least, okay? So you get, you know, a little bit higher lows and a little bit lower highs, right? So a least tidal range with a neap tide, okay? So there's our little orientation geometry of the moon, sun, and the earth patterns in there. Okay, which does affect, so those are astronomical forces that add to kind of together or kind of offset one another and create these tidal patterns, the daily tidal cycles, which can change as the month goes by. But tidal patterns that many factors influence the tides. Your shape of your coastline. Do you have a really steep ocean basin? You know, what's going on for that? Configuration of the basin, your water depth, you know, these are going to have some real effects on, you know, just how high the tides are going to come in. Yeah, so here's one, Nova Scotia area, where at low tide, well, okay, obviously at high tide, the boats came in through here and were able to dock, but look at low tide, you're left high and dry in here. And so they actually have to wait until high tide again in order to get their boats back out. So yeah, this sort of Bay of Fundy, extreme kind of tides, just a daily kind of thing where the highs and the lows are fairly extreme on a daily kind of basis in there. Where being a factor of being able to get your boat in or not being able to move your boat between high and low tides. Okay. So many patterns here, and you don't necessarily have to know all of them. but that they are a variety of patterns that we can see. Diurnal, a single high and a single low tide each day, we would call that. We would see that kind of Gulf of Mexico, along the northern shore of Gulf of Mexico. Just one high and one low. Semi-diurnal, you get 2 highs and 2 lows each day, okay? Little difference in the high and the low water heights, so they're fairly, equal for high versus low. That's a semi-diurnal pattern. Mixed tidal patterns, you get 2 highs and 2 lows, but they're very different. So large inequalities in the high waters and in the low, the heights of the lows as well. We see that along the Pacific coast in the United States. So think out there on California kind of thing, on our west coast by the Pacific Ocean out there. So yeah, you're getting the rise and the fall of tides, these tidal currents. The flood currents are the ones where it's advancing towards the coast zone. Ebb is the seaward moving of water going back out, so the flood and the ebb of that. And you can get these tidal deltas that get created by tidal currents. So as the tide's coming in, the tide's going out, can create these little, fans of kind of deposition called a delta. You remember our deltas from our streams, right? But these are created by the tides, the tidal deltas. I think they might have a picture for us here. Yeah, so here was sort of a barrier island, right? And the tides would come in, the tides will go out, so it can leave and kind of make a little tidal delta in there as well, back into the lagoon, where there's not quite as much movement, right? Where you can get deposition, because that's a delta, a depositional feature. And there you are, Destin, Florida, right, has one where it's going in, the tide's coming in, the tide's going out, and creating a tidal delta, sort of a buildup of sediment, just because of the tides in here. Oh, in this picture, here we are, spring break, Panama City Beach. And if you look at that, really a lot of people out there on the beach, but no one's out in the water. Well, maybe a couple brave souls, but really no one's out there in the water. And it's a good thing, because if you'll notice, they have a red flag. They have a red flag warning. And so this indicates potential for rip currents, right? So very dangerous. If you are planning some kind of a beach trip, well, maybe even this summer or during the spring break sort of thing, pay attention to your warnings, right? So the red flag does indicate that this is a rip current warning. That doesn't mean that there's sharks out there in the water. That is a rip current warning. So heed your warnings on that. So, okay, so that is just a little bit. This does end of chapter 10. So this was the restless ocean. It is a very dynamic interface, the ocean, the land, and the atmosphere. You really can't talk about one without talking about the others, because the Earth is a very dynamic entity and continuously interacting with the other spheres. And so really, in talking about the oceans, we do see that those interrelationships just very closely intertwined. And so that's the end of chapter 10. We will begin our atmosphere portion of the Earth and Atmosphere course. We will be focusing in on the atmosphere and taking a deeper look at that. We've already alluded to it along the way, but we're going to study the atmosphere in much greater detail in those last few chapters coming up. So thank you. And again, if you have any questions on any of this, make sure that you do get with me, and I will see you again soon. Thank you.